Alrighty, y'all. Today we're taking a look at the recitation for February 2nd. Right? And this one we're looking at 1D motion again, just one dimension. Right? So this braking car question, this is a repeat from our last recitation, just in case you didn't get to it. Right? The important part that I'm just going to highlight for today. Right? We're going to revisit this sentence. What is the value of x at the time when velocity is equal to 10 meters per second? Right? Cool. Now we do the exact same problem. Right? A car is traveling at a speed v0 and applies the brakes to slow down to a speed v final. If it is able to decelerate and is at an acceleration ab, how far does it travel during the braking period? Right? So this is the exact same problem that we were just looking at, but this time, oh no, not panicking though. There's no numbers. We're all just working in variables, right? So now let's get an expression for our car position velocity as a function of time. Right? So the first thing, we're told we're given a constant acceleration. So I'm just going to write down our equations, right? X equals x naught plus v naught t plus 1/2 a t squared. Right? And then we have v equals v naught plus a t. Right? Before, we started with this, and then we plugged in our numbers, right, that we were given for each. Right? But now, we don't have very many numbers to plug in. We're given that v naught and v final should be denoted as such, and our acceleration should be AB. That's really all we can plug in, right? We're given that and we're going to set our x naught to be 0 again. So that's just going to make it easier for us, right? X is going to equal v naught times t, right? Just plugging that in. Plus 1/2 AB squared. Cool. Now we have velocity, same thing. Our v final is going to equal plus v times t. Cool. Wonderful. We have our accelerations. Our position, our equations. That's the word I was looking for position and velocity. Right? Now, using the same process we did in the previous problem, we're going to find an expression for how far the car travels during the braking period. Right? It's going to depend on our 3 physical parameters. Right? It's the same process we did in the previous problem, right? So that's where I wanted to highlight this sentence, right? The value of x at the time when velocity is equal to 10, right? So the first thing we have to do is find that intermediate value. We're going to find our time, right? And this equation here, our velocity equation, we know v final, that was given, right, to be v final. We plugged in for that. We know v naught, that was a given, and we know acceleration, that was given. So the only thing we don't know in this equation is time. So let's solve that for time. Okay, so we get v final equals v naught. To make that clear as a subscript, right? V final minus v naught over acceleration is time. Cool. We have our time. Wonderful. Now, this is where it gets a little bit, messy looking, right? The next thing we did is we used the time to plug into our position equation to find the position, right? So now we have this as an expression for time. We're going to plug into our position equation, right, everywhere we see t. X equals v naught times time minus v naught over acceleration plus 1/2 acceleration times v final minus v naught over acceleration squared. Wonderful. There's an expression for our position. I'm going to simplify this one just to make it easier to look at, because right now this looks gross and I don't like it, so I'm just going to simplify it. All right, I'm going to distribute in v naught over all this mess. X equals v naught v final squared. Right, this is squaring this out. So it's going to be square the first minus 2 final v naught plus v naught squared all over acceleration. Now since they're both all over acceleration, I can smush the fractions together. And I'm going to also distribute the 1/2 into this mess. Right, so we're going to get v naught v final minus v naught squared plus 1/2 v final squared minus 2 distributed into the 1/2, so just v final v naught plus 1/2 v naught squared all over acceleration. Wonderful. Now v naught times v final and v final times v naught, one minus the other, the same thing. Ding ding. Alright. Alright. Negative v naught plus 1/2 v naught. It's just going to end up being, right, simplify that. I'm going to be pull this first, 1/2 v final squared minus 1/2 v naught squared over acceleration. Alright, and now since both of these are divided by 2, we can move the 2 into the denominator as well. Alright, so it's going to be x equals v final squared minus v naught squared over 2 is the acceleration. And I know we solved for position, but I'm going to solve for our final velocity just real quick, because that's another way of looking at this equation, right? Just to get things out of the denominator. Okay, so I'm going to multiply both sides. So we're going to get 2 x v final squared minus v naught squared. I don't like that that's negative, so final squared equals v naught squared plus 2 acceleration times x. Fun fact, that's an equation of motion that we're going to want to keep track of going forward, right? We can use that. It's very useful if we don't, to cut out that like intermediate value of time, so we don't have to solve for that intermediate value of time, right? Now let's move on to the next question, a rocket, all right? So we start with a rocket. It burns for 10 seconds at 15 meters per second squared, right? And then it's in free fall, right? And then g equals 10, which hurts my heart, but we'll use it for today just for simplicity's sake, right? So first things first, our acceleration, right? We're told at first the acceleration is 15 meters per second squared, right? Right before burnout ends, right? So we start at our constant acceleration there, right? And then we drop to negative 10 meters per second squared, right? Because gravity's acting downwards, right? So we're going to drop, and now that is constant. Ooh, that is not a straight line. That's a little better. Cool. Now our velocity, right? Since we have a constant and positive slope here, right? We're going to start with, at 0, starting from launch, constant and positive slope like that. Wonderful. And then from here, we're switching to a constant and negative slope that's a little less than our constant and positive slope, right? So it's going to look a little more like that, right? A little bit more gradual than this, right? Because this is a slope of 15, this is a slope of negative 10. So that's that. And here, you can just mark it wherever we end up with a velocity of 0. Actually, that's a little far. All right. I made it a little too gradual. Let's do it. There we go. All right. Still a little bit more gradual to get back to 0, but not as drastic as I did before. Right? Now our height. First, we have our velocity is positive and getting more positive, right? So we're going to start at our velocity of 0. Right? There's our little horizontal tangent line. And our velocity gets positive and keeps getting more and more positive, right? So our slope is going to be positive and increasing, right? So it's going to go positive and increasing, right? It's kind of, I can't draw the graph today, but that's the general gist of it, right? It's going to be kind of look like a parabola. And like if the other half of the parabola was over here, right? There's our parabola shape. Looks really gross when I draw it right now, but trust me, that's what it is, right? And then our slope is still positive, right? Our velocity is still positive for a while. I mean, our slope of our velocity is negative now, but this actual value of our velocity is still positive until we hit 0, right? But now it's going to be getting less and less positive, right? So we switch super duper positive is going to be getting less and less and less positive, right? And we're going to hit 0 around here. So there's our horizontal line, right? It's going to kind of arc up and over. Ooh, this is a gross looking graph by Sydney. I just need a little more space, sure. There. And then after 0, our velocity is going to be negative and getting more and more and more negative as we go, right? More and more and more negative. There we go. So obviously my graph isn't perfect, but the general idea that we want to see, right, is that it's increasing. The slope is positive and increasing here. So this is concave up for those of us that remember our second derivatives, right? Concave up, and then here it's going to switch to concave down, right? Because this is where our acceleration changes, right? So our second derivative of velocity is acceleration. So our concavity switches at that point. So it's going to be concave up, and then it's going to be concave down, right? Because here's our parabola if we just continued it like that, right? Our big parabola out there. We have concave up, and it switches to concave down, but it's still, our velocity is still positive until we hit 0, right? If we launch up at this exact second where our acceleration starts going down, our acceleration is negative and our slope of our velocity is negative, but the actual velocity is still going to be positive until we hit this 0, right? We have to slow down to 0 before we start having a negative velocity. It doesn't just suddenly turn around and drop once it's no longer being pushed up. Cool. That kind of makes sense, I think. It's a tricky thing to figure out, but you'll get it eventually, I promise, all right? All right, so now we have some variables, right? So our acceleration, clearly, throughout all of this, isn't constant, right? This is causing some problems, right? We have a non-constant acceleration where this is causing problems here. But what we can do is we can break it up into pieces and apply constant acceleration during this chunk and constant acceleration during this chunk, right? Kind of like when our car was braking, we couldn't look at before the car started braking because right here our acceleration would be 0, but during our braking period our acceleration was 5, so we could only look at the braking period, right? Same thing as before, right? So we're going to take our first chunk, use our equations on that, and then we'll look at the second piece and use the equations on that, right? So now, how high above the ground is the rocket once the motor burns out, right? So we're trying to find our position, right? Because this time our position is going to be y, right? Just because it's going up and down. So what is the value of our position, right, at the time when our time changes, right? So we're solving for our y is going to equal y naught plus v naught t plus 1/2 a t squared. And I'm going to solve this out with all variables and then also with no variables, just so you can see both, right? So we know we're solving for our YB. That's going to be whatever our final position is at the end of this constant acceleration zone, right? And we're given that our initial position, it's not even a given, we're launching from the ground, initial position is 0, right? And we're also starting from launch, we're starting from the ground, so our initial velocity is also going to be 0 during this time, right? Plus 1/2, and our acceleration, are we given how to mark that? AR, there we go, acceleration of the rocket. AR, t squared. Cool. Then we have YB equals 1/2 AR t squared. Well, we were given how long our time is too, actually. That was my bad, right? Here's our acceleration. Our time that's passing is this tau, which is just the 10 seconds, but I'm going to use tau squared, right? So now we have an equation, right? We don't know we're solving for this. 1/2 is a constant. We're given our acceleration during this time, and we're given this tau. So everything on this side we know. So if we plug in the numbers, we can find our YB. So I'm going to do that right now, right? YB equals 1/2, and our acceleration of the rocket during this time is we're going 15 meters per second squared, right? And we're going for 10 seconds, right? So we're going to find our position. It's going to be 1/2 times 100 times 15 times 100, all right, which is going to be, trying to do this in my head. 15 times 50 is, what's 15 times 50? 750. Right? 750 up from the ground. Sorry, I was asking Siri off to the side. Not sponsored. Right, so that's our position at the end of when the rocket is launching, right? So that's our position up here, right here. There's our 750 meters. Wonderful, right? There we go. Cool. Got an answer. Lovely, lovely. How fast is the rocket traveling once the motor burns out, right? So again, at the time when we burn out, right, after our 10 seconds, we're trying to find this velocity up here. Cool. All right, and we have our equation, right? So our V final, our velocity, just in general, is our V naught plus acceleration times time. Cool. So we're trying to find our, so I think it says VB, velocity at burnout. VB equals our V naught, which again, our V naught, since we're just starting from launch, is 0, plus our acceleration, which is our acceleration of the rocket, times our time, which is again that tau, because that's what's passing that time. Right? So again, we have our velocity of the rocket at that time in terms of two things that we know. We're given this acceleration and we're given this tau. So I'm just going to go over here and plug it in. Right? Our velocity is our positive 15 meters per second squared times our tau, our 10 meters per second. Right? 10 meters per second. 10 seconds, my bad. Right? So here's our VB. It's going to equal 150 meters per second. Wonderful. We have it in terms of variables, and we have it in terms of numbers. Same thing up here. Lovely. We can keep going. How fast is it traveling when it reaches a maximum height? Okay, let's go back up to our graphs, right? So we know that right? At some point our acceleration is negative, right? So we're starting positive. At some point we're going to cross our 0, right? So we have a positive, we have a negative, and we have our 0 here, right? For our position, our height of the rocket, right, we're trying to find this max. We're trying to find our velocity at this max, right? So really we're going to draw our tangent line, and though I'm drawing it poorly, right, that looks pretty close to 0 to me, right? And the reason, right, because when we're going up, we have a positive velocity, we have a positive slope, right? And as we're going down, we have a negative slope, right? So at that exact instant, when we're at the top, we have to switch from a positive slope to a negative slope. We're switching from a positive velocity to a negative velocity. So for that split second, for that instant where we're at the very top, our velocity is going to be 0, right? So that's our answer for this one here. At our y max, velocity equals 0. That's all it is, right? And now we can use this, right, to find the maximum height. So again, we're finding our max height. So we're trying to find the value of y at the time when velocity equals 0, right? But now we're looking at, since we're looking for our max height, we're looking at this second zone now. Now we're looking at our second chunk where we have our constant acceleration, but now it's negative, right? So we're going to find, first, I'm going to pull our velocity equation, right? Because we have to find our, right? So we have, you know what we can use? We can use this equation that we found before, right? This new equation of motion, right? Because we're solving for an x, we have an acceleration, we have an initial velocity, and we have the final velocity, right? So let's go set this up and plug it all in, right? Our v squared equals v naught squared plus 2ax, right? So for maximum height, we can solve this equation for x eventually, but I'm going to start plugging things in, right? We know that we're looking for the position at the time when our final velocity is equal to 0, right? That's what we're looking for, so that's going to be 0, right? For this section, for this new chunk, right, our initial velocity, we're not starting from launch anymore. Now we're considering our initial velocity to be up here, right? Our velocity at burnout. So we can find that, pull that from up here, right? We get our VB, which we already calculated, so you can plug that in after, right? Plus 2, right? And now we have our acceleration down, which is going to be negative g, right, times x, or x, sorry. We're using y for this, right? I can fix that. It's the same thing, right? We're just looking in the y direction instead, right? We know our acceleration is a negative, and it's going to be due to gravity. Wonderful, right? So what we get to do is we're going to solve for y, right? Because this is going to give us our y max, right? So I'm going to bump this to the other side. So negative vb squared divide by negative 2g, right? Our negative is going to cancel out. Give us our y max, right? So I'll move this up, give me some more space, right? So our y max is going to equal whatever our velocity at burnout was squared over 2 times our acceleration, our negative acceleration, which in this case was our gravity, right? But we have an expression that we can plug in for our VB, right? We already solved for that. So we can plug that in, right? I'm going to copy that down. All right, we can just plug in everywhere we see our VB, plug in this. Wonderful, right? So we have our y max equals, right? AR times tau squared, right, over 2G. Cool. This is a pretty simple equation to plug into now because we have this. We remember this from before. We know this because we're given this as well. And we obviously know gravity, right, because that's just going to be our 10, right? So now we can plug in everything that we know, right? So our y max is going to equal, right, so our acceleration at the top, our acceleration going up is 15 times the 10. I'm just going to do 15 times 10, so you don't have to write it out like that, squared over 2 times 10. All right, so 15 squared is a lot. All right, so our y max is going to simplify down to about 1875 meters, right? Wonderful, right? So that is our maximum height. So that's where this is, right? If I extend this axis up a bit, right? I went a little off the page, but here, right, that's our maximum height. That's our y max there that we just found. Wonderful. And how long does it take for the rocket, I'm talking real good today, the rocket to land back on the ground, right? So this, right, this is where, right, since we solved for just our y max, now we're going to solve for all of our, how long it takes, like our time duration for all this. So we know that our beginning section, right, we have our beginning, that's the 10 seconds. My bad. All right, so we're trying to find, in our second section, right, our second chunk of our graph, we're trying to find how long it takes to get from beginning of this section back down to ground. So we're trying to find the time at when our position equals 0, right? So we're trying to find, our time when y equals 0, right? Cool. So we're going to use our position equation. Y equals y naught plus v naught t plus 1/2 at squared, right? And now we can plug in the things that we know, right? So we're looking at our second section. So our y naught, that's going to be our yb, whatever our position was at burnout, right? Because we're starting here. All right, so this is our initial, for this section, we're saying right here, there's our initial y, and then we go from there, right? So that's going to be our y at burnout. So we're setting that equals 0, right? Plus our v naught, right? That's our vb. Again, same thing. That's our velocity at burnout because we're starting at that burnout. Plus 1/2, right? And our acceleration, -g t squared. Right? And we're solving for t. Wonderful, wonderful. All right? So in plugging all this in, I could plug in all of our variables again, right? Because we have yb in terms of variables, and we have vb in terms of variables and all that jazz, but I'm going to be a little lazy, right? I'm just going to plug in the numbers, right? Because I calculated numbers off to the side, right? So we have 0 equals our yb, which was 750 meters, plus our vb, which was 150 meters per second, plus, but it's negative, right? I'm just going to move this negative outside, so it's going to be minus 10 divided by 2, 5 t squared. Cool. So now we have our best friend, a lovely quadratic, right? See, I can't factor this. I'm going to start by dividing by 5 just to make it easier on myself. I can divide everything out by 5. But you know what? I'm going to divide by -5 just to be fun, right? So we can say 0 equals t squared minus 30t minus 150, right? And I switched the order just to be fun and quirky, right? So, and just make it easier to see because this is, right, our A, our B, our C for our quadratic formula. Because I can't factor this, or at least I don't see how to factor it very quickly. So we're going to use our lovely best friend, the quadratic formula. Say it with me if you remember, right? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? And we have a, since I simplified it down a little bit, a is equal to 1, b is negative 30, and c is negative 150. So plugging all that in is not fun, so my calculator does it for me. I wrote a program that does it for me, my calculator, so we get t. Again, I wrote it out with x over here, but since t is our variable in our quadratic, right, it's going to give us the value of t. So t is going to equal 34.36491673. You don't need this many decimals, but I enjoy having this many decimals. And negative 4.36491673. And those, since it's time, those are both going to be in seconds, right? But what's our problem? We have two answers. We're only looking for one of them, right? We're not going to have a negative time, so we can just kind of ignore that solution, right? Because really this is giving us, the quadratic formula gives us the equation, kind of like what I was drawing before, where if we continued this parabola, right, there's where it intersects. If we're saying for this section, our t equals 0 is here, there's our intersection at a negative value. Here's our intersection at a positive value of t. This is what we're looking for, right? So our final answer, all right, how long does it take for the rocket to hit the ground again? It's going to be 34 seconds from burnout, or from launch, it's going to be 44.36491673 seconds, right? From launch, right? Because we have to add, we said that was our time from when the acceleration changes. Right, so we're going to add our original 10 seconds in here, where it launches for 10 seconds, then it falls for 34 seconds. So in total, from launch, it's going to take 44 seconds to hit the ground once again. Alrighty, this was our recitation for February 2nd. Let me know if you have any more questions about this or any other recitation or homework problem or anything else that you want me to try to explain. And I will do my best to try to explain it, because I guess Sydney explains stuff.